All right. Well, hello everybody, my name is Daniel Overbey. I promised Sue 101 slides and Alice 20 minutes, so I'm going to get right into it. I'm an associate principal at Browning Day in Indianapolis. It's a leading architectural firm in the US Midwest. You could have laughed there a little bit. Pictured here are some of my clicker works, some of my marquee projects I've worked on over the course of a decade and a half. But I'm also a building science educator at Ball State University, and happy to be here with Bob Kester, another person from Ball State University. So, and I get the privilege on a weekly basis with students to try to make metrics relatable and interesting, and that's what I'm going to try to do for the next 20 minutes with you all. I was honored and excited when my colleague Alex Wilson, the director of the Resilient Design Institute, contacted me with this opportunity to come and present some work we've mutually been working on, and connected me with Sue, who I actually met 17 years ago. I did the math, 2006, as part of the 2030 Challenge lecture series at the University of Nevada, Las Vegas. You'll see Sue on there with John Reynolds and Plitty Fisk and Ed Mazria. And if you're familiar with Ed Mazria and his work, Santa Fe-based US architect, 2030 Challenge, he kind of gave us a little precursor for the 2030 Challenge the day before he went to LA to give the first keynote on what the 2030 Challenge is. If you're not familiar with it, what Ed called for was for an immediate 50% reduction in the energy use intensity of buildings, and then every 5 years after that, a 10% reduction. Thus, by the time you get to 2030, you're at carbon neutrality. How have we actually done in the States? On one hand, we've made significant cuts in both the commercial and residential sectors. But as you can see here, 26+%, it's not nearly staying on track as a collective industry. It's not deep enough, fast enough. Our model codes and standards in the US have fallen off of our 2030 trajectories. The blue dots there, it's the ASHRAE 90.1 standard, and the ICC is in the lighter blue. That's the International Energy Conservation Code, and their trend lines now set us past the green dot there, past 2030, more into 2040. This is referenced by lots of volunteer green building rating systems such as LEED, and you can see by what they adopt, all of this falls staggeringly short of reaching that mark. If we look at how the industry has done, the signatory firms that have signed up for the 2030 commitment, which is an initiative through the American Institute of Architects, this green line that you see on here, going back to 2010, when this initiative was brought forth to the architectural community, you can see what's essentially a flat line in the last 3 years. You can't read that probably from your seats. That is 50%. What that means is in the last reporting cycle, we are just now, in the 2021 reporting of data, just now reaching the 50% reduction that Ed Mazria called for back in 2006. We've effectively flatlined. And this, by the way, represents the 1,000+ architecture firms that have raised their hand and say, we're going to do this and we're going to report data. This is the best of the best, and also only represents about 0.1% of the firms in the US overall. And of course, you've seen variations of this data, the exponential increase in global greenhouse gas emissions. The US and all of Europe, we collectively are about a third of the total. And of course, we've seen variations of this slide over the course of the last 2 days as well, where implemented policies, again, giving us another flat line. So there has been and will continue to be consequences to the collective flatlining, and this is actually where Alex's story comes in. And I've got the honor of sort of pinch hitting for him and telling you the story of his work in passive survivability, a concept that's been raised here in the last 2 days as well. And that story with Alex goes back to Hurricane Katrina back in August of 2005, where thousands of residents were forced to evacuate their homes due to flooding, and moved many of them, 83,000, toward the Superdome, which is the largest dome structure in the US. And it's funny, on the flight out here, I was watching, just happened to watch an episode of The Greatest of Peyton Manning, Indiana, that's what drew me to it, recounted the 10 greatest stadiums in the world all time, and had this on the list, and they were talking glowingly about what happened here. No, within a day, they had to evacuate people because thermally, in addition to some untoward behavior internally, but thermally, temperatures reached a point that it was unsafe. So 1 day later, folks had to evacuate from this. And Alex and a group of 200 professionals in an event sponsored by USGBC assembled in Atlanta, and put together a product that they used as a sort of a guide map for anticipating this phenomenon would continue to happen, the New Orleans Principles. And within the New Orleans Principles is item number 8 that you see there, passive survivability. This is the origin of that concept that Alex coined here, and you can see the verbatim language. Homes, schools, public buildings, and neighborhoods should be designed and built or rebuilt to serve as livable refuges in the event of crisis or breakdown of energy, water, and sewer systems. That's the original definition. During Katrina, the acute threat was flooding, but we've learned that the chronic threat is thermal stress. And this is something that the headlines, we see it every day. You don't need to look far for it. It's in the mainstream media in the US, as I'm sure it is here. And we're inundated with these headlines every single day. New York Times, this is, you can't see the gray in there, but basically looking at a spiked increase in deaths in the Pacific Northwest attributed to a summer heat wave that we had, and concerns over thermal stress have resulted in institutional guidance for passive survivability. This is not something especially new. Again, that came out of 2010, but in New York City, passive survivability was addressed in some guidance documentation back in 2010. I'm aware too, Alex and I, we sort of keep a database of the standards and guidance documents. The UK also in 2010 had some initial information. I know I'm buzzing through this fast. 101 slides, Sue, so if anyone wants this, I'm happy to share these slides afterwards. 2016 with Canada, New Zealand in 2017, there's a lot of them. Even some newly issued guidance this year, UK level technical guidance on how to adapt buildings to better meet passive survivability. And this is not magic, it's not new, it's about tapping into the natural energy flows of our sites and making sense of trying to reconcile concepts of resilience and passive survivability with sustainable design. That was the initial question posed to Alex and myself, and asking, do they overlap? And when we pursue net zero, we necessarily address both sustainable design and resilient design, but we've largely failed to achieve the basic levels of passive survivability. Why? This is something we wanted to offer to our peers here today. 3 barriers to passive survivability, as Alex, his team at RDI, and collaborators such as myself, what we've ascertained as the 3 primary barriers to why we don't see better performance with building stock with regard to passive survivability. The first being the utilization of climate projection data. Today it's considered best practice to assess one's location looking at the macroclimate, looking at TMY, typical meteorological year data, to ascertain climate normals. You can see with the bars there at the bottom where those data sets are pulled from, TMY, 2, 3, etc. And then you can see the average temperature differentials going back to the mid part of the last century. So you could take, for an example, to put this into a different perspective, take the Windy City, take Chicago, which many might consider to be a predominantly cold weather climate. Oh good, the psychometric chart. I was worried with the gradient not showing up, you wouldn't be able to see this, but if I were to have my students right now design for Chicago, they may very well go to the Energy Plus weather file data, pull this, long-term climate normals from 1991 to 2020, and this is what they're going to be designing with. However, if we were to pull downscaled climate projection data with RCP 8.5 modeled in there, you can see the blue gradient. It gets a little fuzzy with the resolution of the screen, but that's not exactly what I would call a predominantly cold climate. Then this is not what they're designing toward. Some great information, some great research with Arian Laxo and researchers with HDA and the University of Minnesota show that any way that we slice it, looking to the past to design for the future, is not going to be sufficient moving forward. You could take another great example from Boston, Massachusetts, where Alex and I have both given guest lectures and workshops on resilient design through the Boston Architectural College. And in 2004, this project opened up. Boston christened its first ever LEED Platinum project. This is the Artists for Humanity headquarters, and you're probably not aware of this nonprofit, but Artists for Humanity, they serve underserved youth and give them an ability to develop a skill set and to actually develop a skill, an income stream, self-sufficiency, and they do a great service to the community there in Boston. And the building is largely designed for passive ventilation. It was actually designed to take advantage of stratified air for cross ventilation, moving air through it. And what happened was about 10 years after this facility opened up, the facility management team started noticing that the project was not performing nearly as well as it was modeled to or as it had been operating for the first several years. The reason for this failure is pretty evident. You can kind of see the orange gradient there. At the point at which this project was opened versus where we're going in the future, the average number of days above 90 degrees Fahrenheit, you can see the spread there. Going to be all over the board, and with that increase, essentially rendering that passive system useless, which increases the operational cost and causes a burden for this charitable nonprofit. So in order for building project teams to better access this information and start to use downscaled climate projection data, a few things need to happen. It's not so simple as just making it available in the market. There are some other barriers within this one item. It needs to be publicly available through professional or governmental institutions. It needs to be provided in a resolution, scale, and format that's actually suitable for building analysis. And it's got to adhere to some kind of standardized framework. There's lots of different approaches as to how you can actually create this data and bring it to market, and it needs to be codified and regulated. This is something that I brought up with a few folks talking yesterday. Designers are just not going to use climate projection data otherwise. That second barrier, our collective failure in passive survivability. This is the part where Alex would tell you some of his work. I would call it a saga in the US market with regard to passive survivability, looking at a couple of different metrics. The first two, I can buzz through this pretty quickly. Heat index. When the New York Times starts explaining heat index, you know that it's getting pretty dicey out there. But what's interesting about this, it cross-references sensible and latent heat, and with just a couple of degrees and just about 20% difference in relative humidity, for example, you go from a cautious to a dangerous scenario there. You can look at wet bulb globe temperature. Also, an interesting metric that's used in some passive survivability standards, but both of these are designed for outdoor conditions, the latter even assuming activity happening, and it's unsuitable for indoor conditions. So as was brought up by Eliza yesterday, standard effective temperature, this is what Alex and the team at RDI have been working on more heavily, developing this metric, which is suitable for indoor. It takes these other factors of human thermal comfort into consideration, and you can see the passive survivability comfort thresholds offered there. The idea is really simple. You take the worst 7-day stretch in any location for 7 days, that's a long hot or long cold event, and you look at what the degree hours are above or below those thresholds. And you want to keep that number under 216. This is an example from that data presented by NRL yesterday, and you can see in Houston, you don't even get close. But interestingly, you look at that worst cold week, and you don't even get close there. In fact, standard effective temperature has become the de facto metric used for passive survivability at this point, and was utilized by that same DOE report that NRL was working with. They went through that rigorous analysis that Eliza mentioned yesterday, so I can breeze through these slides, but again, looked at 6 representative cities, and the data was pretty compelling. You look at the SET degree hours during those worst case scenarios, and 50% of the total failed to meet passive survivability. What's even more interesting is a third of all FIAS projects, which is the closest thing to a passive house we'll have in the US, also failed to get there. In other words, we cannot insulate our way to passive survivability. We need tools available at the earliest stages of the design process. We once had this when I was going through grad school, when I was doing some of my early research, and even my early years in practice. You might recognize this. That's Ecotech, developed by Dr. Andrew Marsh, and that was out of Cardiff University. Was that my buzzer? Okay, good, I still got time. Good, like I'm just getting to the juicy part. So we can look at passive gains and loss analysis. We could look at passive systems. We could look at a sum path diagram and optimize. We could also look at whole building energy usage. And we could go through quick iterative models. You didn't have to be an Energy Plus grand wizard to access these tools. 75% of firms in the US are less than 10 people staff. Many are far less than that, usually 2 or 3 people. You have to have these quick, accessible tools, and you need to be able to operate in HVAC off mode. A novel concept, and Sue brought this up. When these tools are funded by the mechanical industry, meeting thermal comfort standards developed by standards that are couched in the mechanical industry. Not trying to name names, I could later. That's what you're going to be left with. So we need these accessible tools that allow an HVAC off mode and easily accessible SET analysis, which brings me to the third and final unlock, which is passive systems. This is Harold R. Hay, who actually funded some of my early research at UNLV when I first met Sue. So this is kind of a full circle moment for me. Before Harold's passing, I had access to a tremendous amount of his data, some of which is probably not known to most in this room, except for maybe Bruce and Richard. But you didn't let most of it see the light of day. If you knew Harold, you understand what I'm talking about. We're looking at his 1967 Phoenix prototype. That's the kind of flat line that we actually want. That's measured data from the first year of operation. He scaled it up. Went to a Toscadero outside of UCLA, first full-scale example of this roof pond system. Harold had this idea. Let's take the substance that has the highest heat capacity of any naturally occurring matter on Earth, which is water, and use it as a thermal storage. Even the LA Times tapped into this. There's another flat line. These are good flat lines to have. And then Harold took it to St. Paul, and which is a very cold weather climate, and used a north application where they actually put it inside of an attic space, and it also performed well, so much so that it caught the attention of the Department of Energy. And they ended up issuing a very detailed substantive report published in 1984. And this is a takeaway quote from this: a well-designed roof pond can provide relatively even indoor temperatures year-round, when temperatures can vary between, and you can see I'll use the Fahrenheit here that they quoted, but between 32 degrees, which is freezing, and 115, which is like what you get in Phoenix. We validated this with measured data in Muncie, Indiana, over 2.5 years. We took this information. There's a representative January example, kept it within the passive survivability thresholds with no mechanical systems, even when temperatures were far below freezing. We also looked at, you might recognize this, Los Alamos National Laboratory, Dr. Douglas Falcom, the work that happened in 1984, looking at direct gain, sun space, trom wall, and water wall, solar savings fraction, and the load collector ratio method. These systems work, and we validated it at UNLV with measured data over 2.5 years. It was within 5 degrees of being accurate. There's no reason why we can't utilize passive systems. Again, you cannot insulate your way to passive survivability. We need these tools available to the market, and that's where we're going to operate in this nexus of net zero and passive survivability. And with that, I am probably, there's the 3 critical needs again.